Okay, so in this section, we're going to look at a numerical integration. Right? And the idea behind this is that we have a curve, right, represented by some function over an interval, and we want to integrate numerically, right, using rectangles, right? And the idea behind here is that the base, so the area of a rectangle, first of all, we just have any rectangle, L times width, so the area is length times the width. Right? And so these rectangles, they're going to be all of them will be of the same kind of, they'll be of the same width, right, which we'll call delta x, right? And then the height is going to vary, of course, depending on the function. So the height is going to be some function value, which I'll just call f sub I for now. All right, so that means that the area of each one of these individual rectangles is delta x times the function value x sub I star. All right, and that x sub I star comes from just somewhere in the interval. Right, now there are a variety, and as you can see, to calculate the total area, we just need to sum up all these rectangles. Right, now the choice of x sub I is left up to us. There's different ways you can do this. We can choose the left endpoint. We can choose the right endpoint, which I think we probably covered in Math 1 in terms of the Riemann sum and how that converges to the definite integral. But here we're going to take a look at right, just calculating the numerical value, right, the approximation. All right, and we're going to take a look at two methods, right? Well, three methods. One of them called the midpoint, right? So self-explanatory there. I'll go over that one in a second. Then we're going to jump into the trapezoidal method, which is not a rectangle at all, but a trapezoid. All right, and then something called Simpson's rule. All right, but now first on that list was the midpoint rule. So the midpoint rule is this. All right, so I want to approximate the definite integral from a to b of f of x to be, right, first of all, here's the notation I'll use, m for midpoint, and then sub n. The n is referencing the number of rectangles, right? So that would be denoted by this calculation, delta x, f of x bar sub I, sub 1, f of x bar sub 2, etc., etc. Right? Now, what do these all mean? Right, the delta x is simply the length of the interval divided by the number of rectangles you want, right, which we'll call n. Right now, x, it should be bar here, x sub I bar, so any of these, x1, x2, can be calculating by calculating the midpoint of any given interval, right? So that's the midpoint formula. All right, so now let's take a look at an example here. So it says use the midpoint rule with n is equal to 5 to approximate the integral from 1 to 2 of 1 over x. Okay, so if n is equal to 5, so delta x, as we saw, was b minus a over n. All right, so b being 2. So 1/5 or 0.2. Okay. All right, and then now our x sub I bar. So here, okay. Now, first of all, what does this look like? If we're looking at our interval from 1 to 2, all right. So if our delta x is 1.2, that means here our next one would be 1.2, right? Adding 0.2 each step of the way. 1.4, 1.6, 1.8, and then lastly 2. All right, where here we have our a, which we'll call x0. This one we'll call x1, x2, x3, x4, and x5. Right, in the notation that we've developed here. Okay. All right. So now calculating the midpoints of each one of these, right? So our x1 bar, right, using the formula up here, right? So that means this would be x0 minus x1 all over, or excuse me, plus x1, right? Finding the midpoint. You're essentially averaging out both values. So this becomes 1.2 plus, excuse me here, x0 is 1 plus 1.2 over 2, and that leaves us at 1.1. Okay, again, just by plugging that into our calculator here. So that is right here. All right, and then x2 bar, that would be 1.4, 1.2 plus 1.4 over 2, and then simplifying that, we see 1.3. Right, and then we start to see the pattern here, right? x3 would be 1.5, x bar 3, x bar 4 would be 1.7, and x5 bar would be 1.9. All right, so those are the midpoints, right? And our curve is somewhere up here. It just looks like this. Okay, and the way, this is our 1 over x, it's our function. So that means that our m sub 5, our approximation, is delta x, f of x1 bar plus f of x2 bar plus f of x3 bar plus f of x4 bar plus f of x5 bar. Okay. And then we plug in all these values, right? And again, here, what that means is that when we're choosing the midpoint, that's going to be the height of our rectangle. So here is our height for each one of these rectangles. And again, each one of the bases for the rectangles, is delta x, right? Each quantity here, that's delta x. Oops, one more than I needed here. The width here is delta x, delta x, delta x, delta x, delta x, right? Which is why it's kind of factored here. Right, and the height are these function values. So delta x, f of 1.1, plus f of 1.3, plus f of 1.5, f of 1.7, f of 1.9. All right, and I guess delta x being 0.2. Okay. And then we plug this into our calculator to get a result. Now here is a Desmos, I guess, app or a setup here where we can show you here with a bit more clarity than the picture that I had going here, right? So here's our function 1 over x. You see the curve here, and I'm interested in the interval between 1 and 2, as we see here. Okay, and we have 5, right? N is 5. You see that here as well. All right, starting at 1, ending at 2. And this one is indeed the midpoint, right? And here, if I scroll down here, that's the one that's on, right? Notice that here, if you do right endpoint, you see how that changes. Left endpoint, it would be a different approximation, right? But for our exercise here, we use the midpoint, right? And you can see there, right? If you see the height is where it touches the function, right? And then the associated function value, right? And you see all those here, right? Each step of the way, right? Okay, and then we want to add all these up, right? So here, back up here. All right, and we see here, adding all these up. Excuse me. All right, and we see that the midpoint, and again, this does the calculation already for me, right? It's 0.6919. All right, so we'll say here that adding all these up, we can have this approximately 0.6919, right? And that is an approximation to the definite integral from 1 to 2 of 1 over x dx. Okay? All right, now, a couple things here. How can we make this a better approximation? Well, we can just increase the number of boxes, right? This is 5, but we can just put more in there, right? And you could see here when we're at 5, right, this kind of gap here is not counting, but this kind of gap over the curve is overcounting, right? So it's kind of a balancing out here. That still leads to error, right? But how do we, again, make error less? We just make the number of boxes more, right? And that gives us a better approximation. Right, now here, just kind of working by hand or using some kind of technology, right, we're just kind of limited to how good our calculations can be, right? Ideally, you would use some form of computing device to calculate your numerical integration here.